Our first speaker in this session is Axel Hutt. He will tell us about phase coherence induced by additive Gaussian and non-Gaussian noise in excitable networks. And now I ask Axel to please start his video and his microphone and share his screen. Axel, the stage is yours.
So, thank you, Philip. So hello, everybody. I would like to tell you something about my recent work on coherence in unstructured networks induced by additive noise. So first I motivate the approach or the major idea, then I show a model and two cases, identically distributed and non-identically distributed, and then summarize them. So I'm working in neuroscience primarily, and their noise is a very important issue. For instance, when you want to simulate or model resting or task conditions of a subject, you can do this by assuming a certain thalamic drive. So we modeled this thalamic drive that when we are in resting condition, then there's low noise to the thalamus and there's strong noise to the thalamus when we're in a task condition. So when we do this model, then we find the following. So when we at rest and we are not stimulated by any external drive, then maybe the brain just oscillates at a certain rhythm. Here you can say maybe at hertz. And then you stimulate, you add in resting conditions, so with low noise, you add a stimulation, then you still see the 8, here the power spectrum, you still see the 8 hertz, but there's a small peak with the stimulus frequency. But now we add a strong noise to the thalamus in this model. So we are in the task condition, and then suddenly this endogenous 8 hertz rhythm vanishes and we only follow the 11 hertz. So this describes well the behavior in patients. So in another study, we thought, okay, when we stimulate, how can we stimulate? We can stimulate periodically or by other shapes. So here I show you a mathematical study. The results of that, when you have no stimulation, you have a transfer function that might look like this, f of u. It's a step function, and the corresponding probability density is a peak here. So when we have positive pulses, this transfer function shapes. We can derive this shape analytically, and negative pulses, it also changes sinusoidal. It looks like this. And for random noise, you see the well-known sigmoid shape here, the smooth sigmoid shape. So, and when we assume different shapes of the external stimulation, it's possible to also compute analytically the power spectrum, and then you see the different shapes have different effects. So when you have no stimulation, let's assume our model system oscillates at 10 hertz. And then we apply a positive pulses at 50 hertz. Then we move this endogenous activity of 10 hertz to 12 hertz. So we increase the frequency. When we have negative pulses, we decrease the frequency to 8 hertz. When we apply sinusoidal stimulation, we increase the power, and random noise also we increase the power. So only for negative pulses we can decrease the system oscillation. So external stimulation is quite important, but you can also say, well, the cortex is driven by internal noise sources. So let's say the reticular activating system. So this comes from the brainstem here. And typically, you could model this as noise. So we could ask, okay, what happens if the brainstem activates the cortex with high or low noise level? So for this, we made up a neural model, and we could find that when you have a high noise level, it's similar to the awake state of patients, but when the reticular activating system reduces the input to the cortex, then suddenly you fragmentize the brain. So, and this is a good example or good model for the anesthetic state when you lose consciousness. So when you lose consciousness, then the reticular activating system does not drive the cortex anymore. And so you lose consciousness because you fragmentize the brain. This means that all different areas evolve separately and are not talking to each other anymore. So, and this can be shown very nicely in the experimental EEG and simulated EEG, and they are under these conditions, and there you see they're quite similar. In addition, to understand much better the brain under external stimulation, we took a look at EEG activity. So this is electric activity measured outside the brain under surgery. And we took a closer look at these time series, and we've realized that they are intermittent burst suppression-like activities. So they are silent or low amplitude phases here. And we asked, okay, where does this come from? Sometimes they occur spontaneously. And when we take a closer look, we see here the EEG. This is a focus of one of these intervals that you have high amplitude oscillations and small amplitude oscillation. When we take a look at the power spectrum of the different phases, then we see that this low amplitude activity has an 8 Hertz rhythm, and it's in the power spectrum different from the more or less background activity outside of this small interval. So we can ask, where does this come from? Why do we have an intermittent low amplitude activity at 8 Hertz and otherwise we have maybe just noise? So where does this come from? And in the brain, this might come from reticular activating system because this drives the cortex. So that's the major idea. So we assume that we have this comes out of this study, that external input constant plus noise drives the cortex, and fluctuations in this input to the cortex from the reticular activating system might be responsible for this drop of activity. So we came up with a network model and explained this by reduced input. But now, yeah, maybe I skip this for the sake of time. Now let's come to a model. So we assume that we have a neural model. And so this is a neural network. And this can be summarized. So the topology is like this. We have excitatory population, inhibitory population that excite and inhibit to each other and itself. And we drive the system by noise. And so the model equations look like this. So we have here Vn is the variable, field variable of the excitatory population. W is of inhibitory population. We have here constant driving and noise terms, uncorrelated noise, that we drive the system with the noise. So we have different Gaussian noise classes, so different kind of noise, types of noise. I do not go into too much detail, just give you the major points here. So these random processes that stimulate the network can be classified in noise classes, and they distinguish by their mean and variance. So the network is a Erdős-Rényi network with a probability 0.95. And the connectivity matrix of the nodes is shown here, so they're really uncorrelated. So, and when we compute the connection kernel spectrum, this is quite important. You see that the eigenvalues there's just one eigenvalue that is really large, and the others are almost zero. So this means that, and this large is the constant mode. So the most prominent activity that we can expect is that of the constant mode, where all nodes behave are synchronous. For the case of identically distributed noise, means that the two noise processes Xi1 and Xi2 are both Gaussian with different variances, but different variances, but the same mean, so mean 0. So when we take a look at simulations, here this is the field, 2D field of neurons. And now with time, I increase here the noise intensity. And you see here it's a rather high activity. Well, you see it drop, and now it drops. So at a certain point, at a certain noise strength, the activity drops to a lower value. So this is found experimentally, numerically. And the question is, what is going on here? So when we do mean field analysis, we see here that we find these equations and with new transfer functions, and I'll show you this here. So the new transfer function S1 and S2 is gained from the old transfer function, which is H1 and H2, convolved by a probability density, and this probability density is just the probability density of deviations from the global state. So in our case, we can derive that this is a Gaussian. So we have a convolution of a step function. So H1 and H2 are step functions, Heaviside functions. And this is a convolution, we find sigmoid functions. And now we can understand when we increase the noise level D, so this is then we make the probability density much broader, then, and we take the convolution, then this transfer function, resulting transfer function is more flat. So increasing the additive noise flattens the transfer function and so changes the dynamics of the system. So this can be seen here. So we have for low noise activity, so this is the mean field here. And when we compute the power spectrum of the mean field, for low noise levels, we do not see any peak in the power spectrum, but for high noise levels, we find here a strong frequency component. And the same for phase coherence. So for low noise, we find no peak here at these frequencies, but for high noise levels, we find here high phase coherence. So we have two effects at the end. There's one effect that we have a drop of activity that we've seen in the simulation, and the lower state, so this drops to a lower state, and the lower state oscillates with a strong frequency. So this can be explained here. So at low noise level, we are on a stable node sitting here, and then increasing the noise level, the system drops down here to a lower noise level, to a lower state, and this lower state has different properties. So the stable node, the initial state is not oscillatory, but the lower state is oscillatory, and this is why we find here at the lower state we find here oscillations. And when we look at the linear Lyapunov exponent, we see it here that here this is not oscillatory, so this is a node, and then when we increase the noise level, it drops, and suddenly we have an oscillation frequency and even frequency here. So there's also linked to coherence resonance, of course, because we have the effect of increasing the noise suddenly induces oscillations. And so here, what I show here is the power spectrum of simulated activity, the power spectrum with increasing noise level, and there you see it 0.5, noise level 0.5, suddenly you see a peak. This peak goes to lower frequency and finally vanishes. So noise induces this peak in the power, and we can explain this analytically in our case. And this reproduces quite nicely, qualitatively, but quite nicely, this coherence resonance analytically. So our model is, mean field model is able to do, to explain this coherence resonance. So now we can stimulate in a different way. We do not have to use identically distributed noise, but it's also possible to use non-identically distributed noise. So let's take a look here. When we have now the first noise process has now is a linear superposition of two noise processes. One noise process is a Gaussian noise with mean delta mu and variance d, and the other noise process is has a mean minus delta mu and d. So just for visualization, so the noise processes look like this. If delta mu is 0.5, you see this noise processes, you do not see anything in fact, but it looks quite similar to a standard Gaussian process. But even if delta mu is larger, maybe, yeah, you can say, okay, it looks different, but the statistic properties are completely different. And we see this now in the following plot. So the probability density of this process here for delta mu is 0 is, of course, the Gaussian in black. And when we have delta mu 0.8, you see the two peaks. And this is exactly at 0.8. This is exactly the case of the noise. So when we have such a heterogeneous, non-homogeneous noise process, then we can compute the transfer function. And suddenly now this does not look as a sigmoid, does not have a sigmoidal shape anymore, but now has here almost a plateau here. So it has this sigmoidal shape. So this is so different. So the transfer function is different in the model. So what's going on here? Here I show you simulations. So in the beginning, we are at the upper state, we increase the heterogeneity level, and suddenly it drops to a lower value, to a lower state, similar to the previous case, but now we increase the heterogeneity. So when we take a look at the power spectrum, we see that in fact, increasing the heterogeneity with delta mu 0.8, we see suddenly a peak that was not there before, and a phase coherence is also increased at a certain frequency, similar to before. So the logic is the same. Before we were in a stable node, and increasing the heterogeneity, but we jump or we fall to a lower stable focus here. So this lower state is oscillatory. So, and the same for the linear exponents. And there's also coherence resonance similar to before. So when we increase the heterogeneity in the process here, these are the numbers. You see suddenly at 0.7 here in the simulation, you see suddenly that there's a peak, and this peak vanishes at very strong heterogeneities, and we find a similar, qualitatively at least, similar behavior in our linear, quasi-linear analysis in the system. So we can well explain this coherent resonance for this case. So what did we find? I showed you that increasing additive noise and heterogeneity of this additive noise may induce state transitions to a synchronized state from a non-synchronized state. So, and this jump is also a jump from a non-oscillatory state to an oscillatory state. I showed you that there's an analytical description of these noise-induced transitions. It's possible. There's a similar to coherence resonance, and we have an analytical description of this coherence resonance. And this also explained the burst suppression phenomenon in EG that I showed you before. So in EG, when you remember, I showed you that there are small, short intervals where you find a decrease of amplitude, and this is exactly this case. So we can explain these EG, these drops of activity, these small EG intervals by a drop of a reduction of noise. So to do, so the next steps maybe when we go to, when we take a closer look at the mathematical, at the spatial dimension, we can talk about spatially constrained noise input. And it's interesting to take a look at the stability analysis of general network topography. So here we had Erde-Schröni networks, but maybe it's possible to consider more general networks. And very important, I would like to thank Darren Haidt, Heiko Kaiser from Bern, who provided me the EEG, and my long-term cooperation partner, Jeremy Lefebvre from the University of Ottawa. Thank you for your attention.
Thanks, Axel, for this interesting talk. I'm looking at the questions and any raised hands, but I don't see any raised hands or raised eyebrow. No, also no questions, but maybe one question out of interest. So is there, you talked about how these low amplitude phases, how they could be caused, but do you know what the biological relevance of them is? Are they necessary, or are they healthy or not? Or
yeah, that's a very interesting point. I asked my collaboration partner in Bern, and they said, well, they never these are not known. It's
okay.
not known, and nobody has seen that. And I realized that I found these intervals and realized that there are several of them, and they're really different. And so we thought maybe we can detect them and take a closer look when they occur, because these were data in patients under anesthesia. And so the question is, when do they occur? Are they really relevant? Are they important? Or this is all research to be done.
Okay, thank you.